We're going to see here how an operational amplifier can be used to produce a amplifying circuit. So here we have an op-amp, and we see that it has a feedback resistance that's connecting the output voltage to the inverting input, and we're going to analyze the behavior of the circuit. So we can see that we're going to have zero voltage here at the non-inverting input because we're connected directly to ground there. Since we are assuming a ideal op-amp that is in the linear region because of this feedback, we're going to assume that the inverting terminal, whose voltage is measured there, we're going to assume that that is also going to equal 0, because we're going to assume that these two are voltages are equal to one another. And so that means that we have a voltage of 0 volts here, it's ground, and that's going to be true for this whole node is going to be at 0 volts. We also said that the current flowing into the two terminals is going to be 0, so we don't need to worry about any connection there. We imagine that we have infinite resistance. And so what we want to do is write a KCL equation. Looking at the currents here, there's no current there, so we're going to have current flowing in from the signal source. We're going to have current flowing through the feedback resistor, and those are the only two currents because, again, that current is 0. And so these two currents flowing in must equal 0. We can write nodal analysis equations for each. We have the signal voltage here, minus 0 divided by that resistance, the output voltage minus 0 divided by that resistance there. We can move one of the terms to the other side of the equation, and I can multiply both sides by that feedback resistance, and so I can come up with an equation for my output voltage. And so we see here that the output voltage, the voltage at the output of the op-amp, depends on the signal voltage. There's this negative sign there, that's where the inverting part comes from, and then we have these two resistances. And typically the feedback resistance is bigger, the source resistance is smaller, so this term is then bigger than 1, and thus we get a output voltage that is bigger than our input voltage, and that's where the amplification comes. We're amplifying a small signal and making it a bigger signal at the output. So we have an equation for the output voltage, and like we said, we typically have the feedback resistor being the larger one, so the output voltage is larger than the signal voltage. But we can't just make these two resistors whatever value we want. We can't make them bigger and bigger and bigger so that the output voltage becomes infinitely large, because remember, this whole op-amp is functioning because it has these two biasing voltages connected to it, and the output voltage has to end up being between those two biasing voltages. And so if the output voltage has to be between these two supply voltages, if we take the absolute value of all of those, the absolute value of our output voltage has to be less than the positive supply voltage. But we have an equation for V out. We have an equation right here, and essentially and then if I divide Vs out, then I see a limit on my resistances. These two resistances have to be less than VCC divided by the signal voltage. So usually, again, the supply voltages are around 10 or 20 volts. The signal can be pretty small. Maybe that's the signal coming from an antenna or from a microphone or something, and so you're going to have a pretty small value. You want to amplify it quite a bit, so you can still get quite a bit of amplification, but there's a limit on how big the ratio of these two resistances can be. And if you go beyond that, if this inequality is no longer true, that means that we're leaving the linear region that we were assuming here. And that means that the output voltage saturates, and the output voltage gets bigger and bigger and bigger until it hits the supply voltage and it stops there. And if you make the ratio of these resistors bigger and bigger and bigger, the output voltage just stays at that saturated value. We can do the same thing, but with 3 inputs instead of 1. All of our calculations are the same, but we could have more inputs here. We would have the same op-amp. It's got the same feedback connection from the output to the inverting terminal. We still see that the non-inverting terminal is connected to ground, so this is 0 right here. And so then we have to have 0 at the other terminal as well, because if we're assuming that we're operating in the linear region, which again, this connection gives us negative feedback to keep us in that linear region. Then we've got a 0 there, 0 at that terminal, and that 0 is going to give us, again, 0 all the way through this region. And so same idea as before, this is 0 volts. We have input voltages from 3 different inputs, 1, 2, and 3. We have an output voltage over here. We're going to have currents flowing in from each one of these inputs. And we have a current flowing from our from the output of the signal. The current flowing into the inverting terminal is 0 because, again, we're assuming for an ideal op-amp, there's no current flowing into either of those terminals. And so same idea as before, we have 4 currents that are all flowing in. So these currents all flowing in equals 0. I can write nodal equations for each one. VA minus 0 divided by RA, VB minus 0 divided by RB, and so forth. And then these are known values, so to speak. Those are our signals, and we want to know what the output is. So essentially we solve this equation for VO. We move everything else across the equal sign, which makes it negative. And so we end up with VO is negative all these terms with the RF multiplied through to get the VO by itself. So we have this relationship when we have multiple summed inputs. And so we have any feedback resistance we want. We have any input resistance for each one of those signals. But remember that VO has to stay in the linear region. That was the assumption when this thing worked. So we could have whatever resistors we want. We could have whatever signal strengths we want from the different inputs. But VO has to stay between our supply voltages to stay in the linear region. So each time we work, we want to check to make sure that VO is not getting too large or too small to take the op-amp into saturation. Another thing that we can do here, this was a generalized equation, but we could imagine if we let RF equal RA equal RB equal RC, then what we'd have is something divided by itself gives us 1, something divided by itself gives us 1, something divided by itself gives us 1. So if we are clever with the way we pick our resistances, we can simplify our equation to that. What we have here is our output voltage is the sum of those input voltages, and then of course negated. But we were assuming here that we were using DC voltages, just we've been using constant voltages all around, but that doesn't have to be the case. These could also be AC voltages that represent sound waves, again, from an antenna or from a microphone or something. And so the output voltage here would just be the sum of the input voltages. So if you had different signals for one signal from the microphone and one signal from the guitar pickup and one signal from the bass pickup, you could just add the 3 of those together, and the output voltage would be a combination of those different sounds. And essentially, that's how the different channels of a sound mixer are put together. If you're negating a sinusoidal a signal like that representing a sound wave, inverting that doesn't change anything because it's oscillating so quickly that we wouldn't really notice. Also, we did all these calculations assuming 3 inputs, but really you could sum n inputs, any number of inputs that you wanted. So you could have a 16-channel audio mixer or more. You could have multiple channels for recording a symphony or something like that, and the same general operation would work.